Okay, this will actually be the third video, and what this video is going to focus on is what we call linear regression. And guys, there are other regression models that we can explore, examine, quadratic regression, exponential regression, but we tend to look at the simplest one first, called linear regression. Now, just to put everything back in its proper perspective, what we're doing here is two variable statistics. We call this correlation and linear regression. We've just completed two videos on correlation, which has the purpose of measuring the strength of the relationship between two quantitative variables. So for example, if you have a variable gender, and you want to examine the strength of the relationship between gender and something else, there is a statistical procedure out there for you. It's just not correlation and linear regression. The linear regression, again, focuses on the strength of the relationship between two quantitative variables. What we've learned so far in examining the relationship between horsepower and miles per gallon, I think I summarized it down here. We've seen that there is a linear relationship. The relationship is negative, and it is moderate. So what we're going to do now is we're going to get into linear regression, and I want to give you an idea of exactly what's going on here, okay? If we take data, again, between some generic x and y, and we plot our points, what we're seeking to do here is we're seeking to find the straight line, okay, it's linear, the equation of the straight line that best fits our data. Well, you can see that one probably is not a good candidate. That one is also probably not a good candidate. But there exists one line that if we draw it down through the center of our data, and let me get rid of this stuff down here, it would be the one that it can be thought of, not technically true, but can be thought of as minimizing the distances from the sum of all the distances from the point. Now we talk about minimizing the sum of squares in bigger, broader terms, but nevertheless we want to create the line that best fits the data. So you'll hear me call this sometimes the line of best fit. So gang, if we achieve our goal of taking some data from x and y, and let's say that we just have some generic data here, and we fit this line, what we would be able to do with this is we would be able to make predictions. For example, if we come in with a particular value for x, we could march up to our line, come over to its corresponding y value, and get a predicted value. For example, let's say x is high school GPA and y is first year college GPA. Would someone's high school GPA be a good predictor of their first year college GPA? Well, if you wanted to examine that, you would do correlation and linear regression. You would collect your data, you would analyze the data using correlation, you'd do a scatter plot, you'd find r, you'd find r squared. But then what it would allow you to do is be able to use your model. For example, let's say a student has a 2.80 high school GPA. We could use our model to predict what the person's first year college GPA would be based on their high school GPA. Now, I'll just go ahead and tell you, it probably wouldn't be a very good model, but it's a good illustration. So guys, linear models come in the form of something you've studied before, y equals mx plus b. But because we don't want to just use a value for y, we want to predict y, we put a hat over it. So y hat stands for the predicted y. Now you probably know that in y equal mx plus b that m stands for the slope and b stands for the intercept. Well, I'm going to kind of mess that up a little bit. I'm going to do it for a reason that will make sense later on. I want to change this to the form y equals a plus bx. Now, nevertheless, the y hat stands for the predicted value. The b in this case would stand for the slope, whether we call it m or b or b1 or b hat 1, whatever it may be. The value that goes with the x, in this case the b, that is situated beside of the x will always be our slope, and the other value will pretend there's an e in there. Stands for the intercept. Okay? Alright. Before we start this, we need to go get some things. And remember, in L1, we stored our x's. In L2, we stored our y's. Now, before we start this, we need to find the mean of our x's, which would be horsepower. We need to find the standard deviation of our horsepower. We need to find the mean of our miles per gallon, and we need to find the standard deviation. We also need to find the R value. Well, guys, the R value, we found that earlier. That was negative 0.68. So now it's going to be our job to go to find the X bars and Y bar and so on and so forth. Okay? So we'll use our calculator to find those values. So let's get into the calculator. So guys, let's go to stat. Let's go over to calc. One variable stat. And we'll do the x's first. So I'll go to L1. And I find that my X bar is 231.6 and my SX is 65.34. Okay. Now I want to do the same thing for my miles per gallon, so I need to go into L2. And now it's a little confusing here, but you just have to keep your variables straight. Even though this gives us as X bar equal 20.79, that's actually going to be our Y bar, because we're looking at the descriptive statistics here for miles per gallon, which is our Y variable. Okay? Now, what I want to do here is I want to close this down. I want to go back to the screen, and I want to write this stuff down. Okay? So my X bar was 231.6. My standard deviation was 65.34. My Y bar was 20.79. And my SY was 5.03. Okay? Now these numbers are going to be important because they're going to we're going to use these to find our values for our linear regression model. So guys, our regression model again is y hat equals a plus bx. And it turns out we'll find this one first. And it turns out that we can find our b value by taking our correlation coefficient times the ratio of the standard deviations, making sure that we put the standard deviation for y on top. Okay? So the R value here was negative 0.68. Our standard deviation for y was 5.03. And our standard deviation for x was 20.79. Now, if we can put this in our calculator without doing something really goofy, we will get the value for our slope. So negative 0.68 times 5.03 divided by 20.79. If I did this correctly, oh, wait a minute now. What's going on here? Well, I just messed up, didn't I? The standard deviation, you probably caught this. The standard deviation for x should be 65.34. I would tell you that's the first mistake I've ever made, but I think you know otherwise. Okay? So again, if we go back, we can see that the standard deviation for x was 65.34. For some crazy reason, I decided to use the wrong value. All right, so let's try that again. So negative 0.68 times 5.03 divided by 65.34, and we get negative 0.052. Alright, so verify that on your calculator. Make sure that you get that, okay? So what we know now is we know that our B value is negative 0.052, okay? What I typically like to do in rounding, usually we round to 2 places, but when we have a 0 there, I like to go to 2 non-zero digits. So instead of reporting this as negative 0.05, I like to get a little bit more technical accuracy and go to negative 0.052. Okay? So guys, in terms of getting our model, a plus bx, we have some of it. All that remains is just to find our A. Well, it turns out that our A value is easy to find. It's just the mean for our Y, the mean for our miles per gallon, minus our B value times our X bar. So guys, our Y mean was 20.79. Our B value we just calculated at negative 0.052. Now don't make a silly mistake here and think, well, we've got a negative there. We don't have to include that negative. Negatives are important. Just ask your banker. All right, so we get 20.79 if I didn't do something silly. Minus our B, which is negative 0.052, which is 231.6. Now, I would probably put this in the calculator as 20.79 plus 0.052 times 231.6. Okay? So let me put that in the calculator real quickly. And we get 32.83. All right, guys. So in its most generic form, we have our predicted model. Make sure 32.83. Let's see, 0.252. Now, guys, we've got more than just generic x's and y's here. We have a y value, which we're trying to predict our miles per gallon, and we have x variable, which is horsepower. So we can strengthen up our model a little bit and make it appropriate for the data set that we have by writing it as miles per gallon, 32.83 minus 0.052 times the horsepower. And guys, it's in this form right here that you'll typically see your regression models, okay? Now, I'm not really sure how I'm doing on time. I want to go ahead, I think I'm going to stop the video right here. What we'll do in the next video is we'll come in and make interpretations. So next video, interpretations, and predictions. All right, later guys.